Welcome back my dear students. A very good morning, good afternoon, good evening to all of you wherever you are in this part of this globe. And this is the data analysis and decision making 3 lecture on the NPTEL course MOOC series. And as you know, this total course contact hours is 30 hours, which is split into 60 lectures, each lecture being for half an hour, and the total course duration goes for 12 weeks. And as you can see from the slide, we are on the 30th lecture, which is the end of the 6th week. So, each week we have 5 lectures, each being for half an hour. So, you have already taken 5 assignments, because after each week we have an assignment, and by the end of this week, the 30th one, you will basically be taking the 6th week, which is basically the half of the overall course which will be over. And obviously, after the total number of assignments will be 12 in number, and after the whole course is over, you will be taking the final examination. So, if you remember, we are considering the concept that artificial variables will be important in order to forcefully ensure that there is one basic feasible solution, because all of the variables which are 0 and the non-zero would definitely be positive, which is one of the main conditions of the assumptions for the linear programming problem which we have considered. And based on that, we basically start off the process of the maximization and the minimization problem, depending on which is the entering and the exiting variables, that is a different question. And we also ensure in the objective function the weights which you are going to give for the maximization or minimization problem for the artificial variables would be, for the maximization is as low as possible in negative sense, because we are slowly going to increase our value of the concept of the objective function till we reach maximum, and in the minimization problem we will keep it as high as possible in the positive sense. So, we will basically start decreasing the values from the high value to the minimum value which is ensured. Now, I also showed that the starting basic feasible solution for the considering the artificial variables would be the case where the artificial variables would be non-negative some values, such that initially we had a value of 11 by W and basically continued doing the calculation till we are in the last stage of the problem which we are basically solving. Now, in this problem formulation, we already have x1 as a decision variable which is non-zero, x2 is a decision variable which is non-zero, x7 is there as a decision variable which is very high. Weightages will be there for the objective function, because W is very highly positive, because it is a minimization problem, and we will try to basically find out if any improvement can be done from the third tableau, and basically we are able to achieve the goal of trying to minimize the overall problem. Okay. So, this slide I should basically so I should have basically shown this, sorry for that. So, once we basically decide, so which one will be the exiting and the entering one. So, now I consider the corresponding pivot row and the pivot column, I will mark them. So, this is the pivot column, this would be the pivot row, and the pivot element would be this one, which means, so this is just the general structure of how we do find out the pivot row and the pivot row column and the pivot element for the mixed maximization and the minimization problem. Now, the moment the pivot row and column is decided, it means x5 will enter, that means one of the artificial variables will enter, and x7 which is basically the one of the the slacks and the surplus will enter, and the artificial variable which was still existing in the solution x7 will go out from the system. So, once we basically do that, our actual solution basically becomes this, which means now I have x1, x5 and x2 as the basic, and which are non-zero, and the corresponding values of x3, x4, x6, x7 and x8 would all be 0, as it should be, as this is given. So, when I try to find out x1, so the corresponding column wise we will find they are 1 0 0. When I try to find out x5, column wise it is 0 1 0 as it should be, and when I basically try to find out for x2, it is 0 0 1 as it should be. So, when I want to find out the corresponding values of x1 is 0.6, x5 is 1 and x2 is 1.2, and the other values of x3, x4, x6, x7 and x8 are 0 as is it. So, in the problem formulation, when I basically write it down, I have x1 as 3 by 5, x2 as 6 by 5, x3, 4, 6, 7 and 8 are all 0, x5 is 1. So, when I put it in the objective function, so x1 is 3 by 5, so it will be 2 into x1 which is 6 by 5 as it is, x2 is 6 by 5. So, this is objective function is x2, so it is 6 by 5. All other variables x3, 4, I am not coming to 5 immediately, 3, 4, 6, 7, 8 are all zeros as it is, x5 even it is 1, it is being multiplied by 0, hence the total value for that is 1, 2, 3, 4, 5. So, this is the value. So, 0. So, the total objective function has now become 12 by 5. So, that means, I have basically been able to minimize the problem to the value of 12 by 5. Now, it means that they would be at this stage the optimum solution. So, there would not be any exiting variables and entering variables. So, the actual objective function we have ensured that considering the artificial variables in the problem formulation, we do get a solution which basically guarantees an optimum value in the minimum case, maximization case also we can have the same thing, but it has ensured that the starting basic feasible solution which we started adhere to the properties that if any of these the variables were non-zero, they were basically positives, hence it was possible based on the assumption to start our overall search procedure from that particular point. Now, with this I will basically go into another area which is more of a again a discussion, but I will give you a background. So, consider that you are one of the transporting companies in India, and this problem would be considered as the concept of transportation problem. So, you are a transporting company, consider you are the Food Corporation of India, or say for example, you are one of the car manufacturers, maybe Maruti, maybe Tata Motors, maybe Mahindra, whatever it is, or you are basically one of those retailers which basically supplies goods from one part of the country to the other part. It can be Flipkart, it can be Amazon, it can be, you can be one of those consumer goods like trying to basically produce fridge like Godrej, or it can be Whirlpool, whoever it is, and basically trying to transport at different parts of the country. So, what we will consider, there would be some origins from where the products are basically transported, and there would be some destination. If you remember, I have discussed that and drawn the diagram where you have basically a set of m nodes or n nodes as it is on the left hand side, and there are m or n number of destinations on the other side. So, we will basically say that they are set of origins. Total number of original points are m in number. So, if I am allowed to draw, so basically I will try to draw it, it will be easy for. So, I have different type of, okay, I won't mark it, I will mark. So, you have 2, 3, 4, these are the origins, you have the destination 1, 2, 3, 4. So, the contacts are happening like this. And third one, so it looks cluttered, but generally this is how the network system is being drawn. And obviously, they can be intermediate positions also, like another sets of destination or distributors, then it goes in the retailers, but we will consider them as it is. So, the total number here is m, total number here is n. Now, as you are transporting the goods, there are two important things to remember. Number one is, what is the cost structure for transporting from the ith one in the m set of origins to the jth one in the set of j number, j being the suffix corresponding to the n number of destination, point 1. So, that means what is the cost structure, now, which would be given. Point 2 is that, which is more important, we want to find out that what is the total quantum of products which are being transferred from the ith one to the jth one, where I is equal to 1 to m on the left hand side and j is equal to 1 to n on the right hand side. Now, you will basically have two such different matrices. It should be remembered that the cost structure would be given to you, while the values of the transportation or the total quantum of the products which you will transfer from the mth origin, m number of origins to the n number of destinations, you have to basically find out based on some principle. So, what is that principle? We want to come to that within 2 minutes. So, here is how I have drawn the overall matrix. The matrix is like this. So, on the left hand side we have the origins. So, the origins are marked 1, 2 till ith one, then it goes to m minus 1 into m, and the destinations are marked as 1, 2, j 1 till n minus 1 into n. So, you as the diagram showed, m number on the left hand side, n number on the right hand side from my side. Now, the total quantum of goods which is being transported from the first origin to the first destination is given by x suffix 1 1. So, this dash 1 comma 1 is the suffix. So, that means I am transporting x 1 1 quantum of goods from the origin 1 to destination 1. Similarly, I am going to transport x 1 2 amount of goods from origin 1 to basically destination 2. Similarly, I am going to transport x 1 j from origin 1 to jth destination. The second number is second last number is x 1 comma n minus 1 is basically the total quantum of goods which I am going to transport from the first origin to the nth minus n minus 1 destination, and to the final nth destination the total quantum of goods supplied is x 1 comma n. And on the right hand side I write a value of a 1, which means the total number of such goods which is being supplied from the first origin, if I add them up, that is x 1 1 plus x 1 2 till x 1 j, and then continue till x 1 n minus 1 and x 1 n is equal to a 1, that is point 1. Similarly, if I see the ith origin, from ith origin I am transporting to the first destination x I 1, to the second destination x I 2, to the jth destination x I j, to the n minus 1th destination x I n minus 1, to the nth destination x I n, and the sum of all these, that means x I 1 plus x I 2 dot dot till x I j, then dot dot till x I n minus 1 and x I n is equal to a suffix I. When I come to the m minus 1 origin, the total quantum of goods being multiplied, I am going a little bit slow, I understand, but let me explain. So, the total amount of goods being transported from the m minus 1 to the first destination is x m minus 1 comma 1, to the second is x m minus 1 comma 2, till the jth one is x m minus 1 comma j, to the n minus 1th destination is x m minus 1 comma n minus 1, and the last one would basically be x m minus 1 comma n. If I add up all these values starting from x m minus 1 1, x m minus 2 2 till the last one, second last one, which is basically x m minus 1 n minus 1 plus x m minus 1 n, basically gives me the value which is on the right hand side is a suffix m minus 1. Now, if I go to the last origin, the total quantum of goods being supplied, I will not call about the destination, is x m 1, x m 2, x m j, x m n minus 1, x m n, and the total value if I add up is basically a suffix m. Now, if I add up all these values, this is the total amount of goods which is being supplied starting from the first to the mth origin, and the total sum would be a suffix 1 plus a suffix 2 till the second last one is a suffix m minus 1 and the last one is a suffix m. So, the total amount is what I am being transporting from all the origins which is there on the left hand side. Now, let us check concept of the values when I am looking from the destination side. So, when I am looking at the destination side, destination 1 is getting goods from all the m number of origins. So, the first quantum which it gets is x 11, x 21, x I 1, the second last one is x m minus 1 1 and the last one is x m 1, which that means for the first destination the total concept of the total addition which I get if I add them all up, this one is b suffix 1. So, total destination 1 needs b suffix 1 quantum of goods which is being supplied by all the origins. Similarly, origin 1 or origin 2 is basically supplying to all the destinations. So, there is a mutual understanding between supply and for the destination and the origins. Similarly, for the second destination, the quantum of goods which is being supplied from the first to the mth destinations are basically x 1 2, x 2 2, x I 2, x m minus 1 2 and x m 2. So, the total sum if I add up for destination 2 basically comes out to be b suffix 2. Similarly, for the jth one, the values are x 1 j, x 2 j, x I j, x m minus 1 j, x m j and the total value if I add up basically comes to b j. Similarly, when I come to the nth minus 1, the values are x 1 n minus 1, x 2 n minus 1, x I n minus 1 till the second last one which is x m minus 1 n minus 1 and the last one is x m n minus 1. Addition of all these things basically comes out to b suffix n minus 1 and the last basically destination which is the nth one, the quantum of supply which is happening for each and every origin from 1 to m are correspondingly like this: x 1 n, x 2 n, x I n, x m minus 1 n, x m n and the total value if I add up basically comes out to be the value of b n. Now, very interestingly, the total value which is being sent from the destination is basically b 1 plus b 2 till the last one which is b n. Now, if there is no extra amount being transported from either of the origins and no extra amount is basically be demanded by the destinations, if there is an exact balanced equation like in a bucket, water is entering, water is going out, and if I consider the amount of water spillover is 0, obviously it means the input and output balances out. In this case, the sum of all the A's should be exactly equal to the sum of all the B's and that will be utilized as one as the main constraints or main condition based on which we will basically try to optimize our problem. So, now this is basically the quantum of the amount. Now comes basically the cost structure. So, the cost structures I have again written in the same way. The cost structure being of transporting from one origin to one destination is C 1 1, from one origin to the second one is C 1 2 till the last one which is from one origin to the nth destination is C 1 n. Similarly, for the second origin the cost structures I will only repeat the first and the last one values is C 2 1 and the last value is C 2 n. Similarly, for the ith origin the values are I only repeat the first and the last cost structures is C I 1 and C I n. And similarly, if I consider the mth origin corresponding to the destinations 1 to n, the cost structure is C m 1. This all these values we are I am reading out after the x's or the c's are all in the suffixes. So, it is C m 1 till C m n. Now, these cost structures are known to me based on which we will basically formulate the problem. So, what is the problem we want to solve? Our main problem formulation would basically be to minimize the total transportation cost based on the fact that x I j is the amount which is being transferred from the ith origin to the jth destination multiplied by C I j, where C I j is the cost of transporting one unit of product from the ith original to the jth destination, where I is equal to 1 to m, j is equal to 1 to n. So, this is the problem formulation: minimization, double summation, I is equal to 1 to m, j is equal to 1 to n, C I j, x I j, and I want to basically minimize. So, remember it is basically a linear programming problem which you have done. So, hence the minimization problem as given is C 1 1 x 1 till C m n into x m n. Remember, m and n need not be equal. In one case it can be m is greater than n, in another case it can be basically n is greater than m, and obviously if m is equal to n, then in that case you will basically have a symmetric matrix. Now, what are the constraints? As I mentioned, the sum of each of the rows corresponding to origin 1, all the amount which is being transported to all the destination adds up to A1. Similarly, for the second row, addition of all the amount which is being transported from the origin and 2 to all the n number of destinations would basically be A suffix 2. Similarly, for the last row which we will have is basically which is being the total amount which is being transported from the mth origin to all of these destination 1 to n, if I add up, is basically becomes exactly equal to A m. So, here I have the equations corresponding to the rows, and how many such equations there are? There are m number of equations corresponding to the m number of origins, that means there are m such constraints in the first set. Now, let us go to the column wise. So, column wise is basically we have the destinations starting from 1 to n. So, the summations would basically be x I j, but here I is equal to 1 to m, but I am basically trying to count for all these things. So, x I j and I is equal to 1 to m would basically be equal to b j, which is the values which is given at the bottommost row. So, it is b 1 to basically b n, and that values should always balance. So, I will basically have summation x I j, I is equal to 1 to m is equal to b j, j is equal to 1 to n. So, now I have in the objective function there is only one objective, constraints are m and n, that is m plus n, and based on that we have to basically solve the problem. Now, remember here equality sign is there, obviously we need to basically add artificial variables if required. So, the total number of artificial variables now added would be m in the first, n in the second. So, that will be m plus n. In case if the constraint was such that the total amount was less than equal to or greater than equal to, then in that case we will basically have the slack and surplus and formulate the problem accordingly, and then basically solve both in the artificial case, variable case, as well as in the slack and surplus case the problems correspondingly. Remember here x I j's are all greater than 0, I is equal to 1 to m, j is equal to 1 to n. Now, here the actual problem formulation is we have one the left hand side. Okay, another thing which is very important. If I add up all the values in all the cells for the matrix which basically denotes the total quantum of transportation which is going to take place from each and one of these origins to the destination, which is basically x I j, and you are basically going to sum up I is equal to 1 to m, j is equal to 1 n. That should also be equal to the concept that if I sum up all this x I j, but I do first the summation from I is equal to m and 1 to m, and then I sum them up from j is equal to 1 to n, the values should exactly be equal to the either the sum of all the a's or the sum of all the b's, such that if the balance is there, there is no spillover, there is no loss, there is no demand which is unmet, or there is no supply which is basically extra supplied, then the summation of A 1 to A m dot dot till A m will be exactly equal to B 1 to B n, and basically adding up all these values accordingly. Now, what is important to note down is here, to solve this problem there are different methods, and I will only discuss the methods very simply. They are just the simplex method we could have used it, but these methodologies gives us much better starting and very good approximation in the beginning. So, one of them is basically the Vogel's approximation method. The second one is the northwest corner method, that means you go to the northwest corner method and basically balances accordingly. Other is the row minimization rule, that means basically consider on each of these rows. Rows means the origins which you are going to consider. One is basically the column concept, which where you basically concentrate on the concept of the destinations, and one is the basically the base rule, which is the thumb rule is on the inspection methodology based on which we do. Now, what is the general Vogel's approximation? I will come to that later on, but let me give you a basic preview. So, what you want to do is that consider that you are looking at any of these originals. So, origins you want to transport. Now, once you want to transport, what will you look at? Your main concern would be to look at any one of the origins where the demand has to be met the fastest, point 1. Point number 2 is that when we meet the demands, we also want to meet the demands at the fastest as the destination based on the fact the cost is also the lowest. So, you will basically try to choose the vector corresponding the cost, the cell value which is the least, and also try to basically pick up that particular row for which the demand has to be meet the fastest, because if you are not able to meet the demand, there would be unfulfilled demand. So, as this is a minimization cost, remember. So, as this is a minimization cost, I will basically choose the one for which the cost structure is the least and where the demand utilization would be the maximum at the fast. But there is a catch. The catch is that consider the first origin basically has 400 number of units to transport, and consider and it basically supplies, it should supply to say for example, either the destination 1, 2, 3. Now, destination 2 considers the cost is the least. So, you obviously will basically supply all the goods from origin 1 to destination 2. But now, because for the cost structure, but now consider the whole of the goods are not met at the destination, which means that immediately we will supply all the goods from origin 1, and the extra one which is still left will basically try to supply from the next minimum origin, such that the cost structure we try to basically increase it. The cost structure obviously will increase, but will increase in the least quantum jumps, because CIs are the unit cost which you are going to basically add up for additional amount of transportation of 1 unit of element from one of the origins to one of the destinations. So, if it is Cij, so Cij basically means I am basically trying to transport 1 unit from the ith origin to the jth destination. Now, if your cost structure, if you could basically look at the other way also, that means rather than considering only the rows, we can only look at the columns. That means basically I will try to minimize my overall concept from the column wise, such that I will consider that the cost structure which is minimum from the column wise, and then I will basically try to meet and get all the demands from the origin which is basically the minimum cost. So, in this way what I am trying to do is that either I look at the destination point of view or I look at the original point of view, based on the fact I only consider the cost as the main prerogative based on which I am trying to minimize. But also remember that if there is some unfulfilled demand of there are excess demand both at the destination and the origins, we will try to basically consider that in such a way that the balancing would be done. So, the Vogel's approximation, northwest corner method, or the row minimization and the column minimization would basically consider this concept in order to basically optimize, considering that optimization fact is that we want to basically minimize the cost. So, with this I will close this 30th lecture and basically start off the Vogel's approximation, northwest corner, row minimum and the column minimum method and the inspection method in the 7th week starting on the 31st lecture. Have a nice day and thank you very much.